All right, back for more. Welcome to Thursday. What we're going to do is we're going to go over the test. I did post the grades on that. That's part of the midterm grade, so I think you should be able to see the midterm grade. I'm not sure when they post those, but you can check that out if you want to know what it is. So let's go through the test real quick and then see if you guys have questions, and then we will proceed through some more sections of chapter 12. Today is like continually flying through this material, and I know it's quick, but we'll talk in a second about more strategies, I guess. Okay, so number one was just a bunch of complete the squares. So it said to find the center and the radius of a sphere, and I'm not going to write the whole equation down to start with, but it had an x squared and a 6x and a y squared and a 12y, and it had a z squared and a minus 10z. It also had a 63, and this is where people are just making little errors when they try to figure this out. You bring the minus 63 to the other side. Right off the bat, that like screwed people up, putting it as a negative 63 on the right, because you want to complete the square by adding half of the middle one squared. So 9, and then this would be adding 36, and then this would be adding 25, plus there, 25. So if you put those things together, it's 70. So if you add, you're basically adding 70 to both sides so that you can condense this into x plus 3 squared and y plus 6 squared and z minus 5 squared equals 7. And so you just have to reel off that the center is at minus 3 minus 6, 5, because there's built-in negatives into the formulas, and the radius is the square root of 7. So that's on the right side is the radius squared. So you could, I suppose you could draw that if you wanted to. 2, x equals y squared plus z squared over 9. Now, if you set y to be 0, so these are these things called the traces or level curves. It just means you want to condense from 3D down to 2D. And you have to look at it from 3 different directions and hopefully be able to piece them together into a picture. It takes a little bit of practice. So if y is 0, then x is z squared over 9. If z is 0, then then yeah, x is equal to y squared. So those are both parabolas. And if x is 0, well, the problem with x equals 0 is you get 0 equals y squared plus z squared plus over 9, which is actually just a point 0, 0, 0. The only solution to that is 0, 0, 0. So you really wanted to look at the level curve, say when x is equal to 1 or x is equal to 2, because then you got 1 equals y squared plus z squared over 9. And now you start getting ellipses out of this. So it's like parabola, parabola, and then ellipse. So if you try to put all those together, well, it depends on which axis you want it to be up. If you, let's see, if you did x, y, z this way, then
hang on just a second.
Then let's see. So it looks like a parabola, x equals y squared, x equals z squared, and then you have an ellipse. So it looks like a spun parabola, almost like a spun parabola, except it's a little bit stretched out because it's not a circle, it's an ellipse. So we just call this a parabola. So that's the answer for part A, anyway. For part B, 2B here, this is x squared plus y squared equals 1 plus z squared. If you set z to be 0, then you get x squared plus y squared equals 1, which is a circle. If you set x to be 0, then you get, well, if you bring everything over, you'd have y squared minus z squared equals 1. So x is gone and you bring the z squared over. If y is 0, you'll have x squared minus z squared equals 1. And those are both hyperbolas. Hyperbolas or hyperbolae. And so if you try and put those together, x, y, z, then it looks like a circle in the xy plane. It looks like a hyperbola in the xz plane and in the yz plane, or in the YZ and XZ, they look like hyperbolas. There's one coming out of the board that's hard to draw. If you wanted to draw also when Z is, say, either plus or minus 1, then that means you either go up 1 or you go down 1. You'll have x squared plus y squared equals 2, which is also a circle. It's just a bigger circle. So you get another circle which is bigger. And maybe at this point you're like, okay, I can kind of see it. Looks kind of hourglassy, and this is called a hyperboloid. And actually, to be precise, it's called a hyperboloid of one sheet because it's connected. It's like a water or nuclear power cooling tower. So, yeah, those take practice, to draw all those things out, but they're really just all these conic sections put together as best as you can.
So you don't do the whole thing, sorry, where it's, where you divide by d? Like in the textbook, it was saying like, you said one, the vector, the variable you're solving for as d, and then like divide by it.
It's possible. I'd have to. Maybe let's come back and I'll look that up and see what's going on there. I think it's possible that it's trying to say, let's try and do any traits. Maybe, I don't know if this is exactly what you mean, but if you said x equals k, like you don't know what k is, but at k level, if you were to stick that in, you'd be x squared plus y squared equals 1 plus k squared. And no matter what k is, those are all circles that are getting bigger as you go up. So it's like circle, a bigger circle, and actually plus or minus k will work, so you'll also get a bigger circle that way, a bigger circle. So if you connect them up, you start to get something that looks like that. The division part could be when you're trying to work it out and you want to get hyperbolas, you got to make sure that the right-hand side is 1. In a circle, it's the radius squared, so you don't really care, but in hyperbolas and ellipses, these both have to be 1, so you're going to have to divide out in order to get it. That's possible. That's possible. So you can look at that later. 3, the only comments on 3 is don't round so much. If you round, maybe you do that in nickels, I understand. This is virtual Mallory Hall, so let's keep things as precise as we can. Because once you start rounding, your answers just become gibberish after a while. So, so U and V are given as 2 vectors, and it's just, the first part is just, can you calculate with these things? So the length of U is, you square all these, 1, 1, 1, and you add and take the square root. So square root 3, just leave it. The length of V, you square all of them, making sure to square the negatives out. If there's still problems with that, I don't know how to fix that. Just use parentheses or something. Square all those, 25, 16, and 1. You add them up, you get square root 42. Just leave it, square root 42. Don't write 6.08 because that's wrong. Or whatever you wrote down is wrong, because if you squared it, you wouldn't get back to 42. It would be only an approximation, and there's no reason to do that here. The numbers are so simple. Now, U plus V, that means do the inside first. Add them together first. So if you add, you get 6, 5, minus 2. Now do the length of that. You can't just add square root of 3 and square root of 42. It doesn't work that way. And so you end up getting square, 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 square root 65. So you get a square root 65. U minus V is you subtract them off, so you get minus 4, minus 3, and 0. Be careful on that, because it's minus 1, minus a minus 1. Square, square, take the square root. Now, this one is square root 25, so you're not rounding by just taking the square root to get 5, so that's not a problem. And then the last part you got hammered on, if you wrote U dot V is a vector, that's absolutely a huge misunderstanding. The dot product gives you a number. The cross product gives you a vector. So please figure that out for the final. So you multiply the components. That'll be 1 times 5, 1 times 4, -1 times -1, and so the answer is 10. So that was it. That's for part A. Part B, since we have all the components here, part B is the cosine of the angle between them is the dot product, 10, divided by the length of each vector multiplied together. So square root of 3 times square root of 42. Dot product on the top, length of U, length of V, multiplied on the bottom. And honestly, you could just leave it as the arc cosine of that number. It's not pretty, but I understand what that means. You don't have to calculate it out and screw up the rounding. So just leave it as the arc cosine of 10 over the square root of 3 times square root of 42. Part C was projections. So I think most people got this one right. You take V and project it down onto U, then it's basically, it's a multiple of the vector U. So I know it's going to be some number times U. That number is the dot product divided by the length of U squared. So 10 is the dot product, the length of U is square root of 3, so you square it and you get 3. Leave it. Don't write 3.33 because that's not right. You multiply 3.33 times 3, do you get 10? No, you don't. So your answer is wrong. If you want to write approximate, I suppose that's okay, but you don't need to in this case. U projected onto V is a multiple of V. So what multiple is that? It's the other one. So it's the dot product divided by the length of V squared. So we get that. D, this is, I mean, it's a kind of big issue. If you screwed up D, you're just missing, I don't know, you're missing something. You have the book, you have the formula, so if you don't understand the formula, that's one thing. If you do and you just screwed it up, I don't know what to say. If you wanted to be careful on this, then it's going to be I, J, and K. The J has a negative, the K has a positive. For I, it's going to be the lower determinant here. So 1 times -1 minus 4 times -1. That's kind of small. -1. Not any better. For J, it's B, so it's going to be 1 times -1 minus 5 times -1. And then K, it's the ones down here. 1, 4 minus 1 times 5. And so if you write that out, it's either going to be 3I minus 4J minus K, or if you want to write it in vector format, 3 minus 4 minus 1. E, it says take that answer and cross it with itself. So take U cross, do the parentheses first, you get this vector, cross it. If you just wrote, well, that's equal to 0 because they're parallel. They're the same vectors, so they're parallel, therefore the cross product is 0. That's it. You could work it out and also get 0, 0, 0, but that's a better understanding of that. I'm not sure anyone did the extra credit, but that's all right. It's extra credit. 4, if you've got P and Q and R out there, and you wanted to figure out what the triangle is, then if you find PR and PQ, cross them and take the length, that would be the area of the parallelogram. So to get the triangle, you just take half. The area will be 1/2 the length of PR cross PQ. And it doesn't really matter if you do like QP cross QR, or just make sure that you have the vectors coming out of the same point. So let's see, so that's 1/2 from P to R. That was 5, 4 minus 1, and PQ, which is 1, 1 minus 1. Now, if you said, well, I did the cross product, but they're in the other order, well, that'll reverse the direction of the cross product, but it won't change the length. So it doesn't matter which order you do these in. If you do the cross product this way, you will get minus 3, 4, and 1. And again, if you did it the other way, it would be 3 minus 4 minus 1. But the answer won't matter. When you take the square root, the squares of all these, you still get square root 26. Divided by 2. Leave it. You want to write it out? At least write approximate. Don't write equal because it isn't. 5, probably squeeze a bunch more in here. 5 was a little trickier, but the point is the line will be the base point 5, 1, 9, and then you have to figure out what the direction of this is, and then multiply each of those things by t, and you'll add on the multiple of t. And so it says it's orthogonal to 2 things, and if you have 2 things you want it to be orthogonal to, you take the cross product. So your direction will be d1 cross d2. So you take the 2 vectors that you're given and cross them together. Actually, all you get is just minus j. So that means that this will be plus 0t minus 1t and plus 0t. Or if you prefer, you can just write that as 5, 1 minus t, and 9. And that's the equation along in vector format. Part B is distance. So the distance formula says that it's PQ cross D over the length of D. And D is just minus J, so the denominator is 1. The distance from the line to the origin, well, we could just pick P to be the base point. So if P is the base point, then we go from P to Q, which is the origin. That's just minus 5, minus 1, minus 9. And then you cross them, and then you take the, so you take the cross product, and you get like minus 905. You take the length, it's 106, take the square root. Yeah, technically a little bigger than 10, but just that's the correct answer. 6, find the equation of a plane. It's something times x minus the base point coordinate, something times y minus the base coordinate, something times z minus the base coordinate equals 0. So at least that's the template for the equation of the plane. You can take any of the points you want. Might as well just pick 519 first. And then the numbers in front are the normal. And the normal is just any of these 2 vectors, say PQ cross PR. So you find PQ, find PR. PQ will be minus 4, minus 1, minus 8. Take the cross product with that of minus 3, minus 1, minus 6. Should get minus 2, 0, 1. And therefore, those are the points in front, minus 2, 0, and 1. And I guess you could multiply some stuff out and combine and move the numbers over and maybe clean it up a little bit. But at least if you write it out here, you can see the point and you can see the normal. So you don't have to. I wouldn't recommend it. Anyway, that's the test. And so again, the midterm grade, like to see. Test 1 is 14%, test 2 is 14%. There's 28% done. The homework is 14% total, and so far, maybe around a half of that, maybe a little bit more. Maybe we've done about 7% for the total grade. So we've done about 35% so far of your total grade. Which means you have test 3, test 4, the final, the rest of the homework. If things are going well, good job, keep it up. If they're not, still have about 65% of your grade left to go. And some of you are not turning in homework. And I know that there's a lot and you've got a lot on your plates, but that's basically throwing away, you're at like a 86% to start the class, and then if you do 80% of that, you're at like 68% total on that. I guess that's a pass, but that's going to be not the best way to go about it. So get caught up and send questions, send me email, send text, ask questions in here. Go to the OML, so the Open Math Lab. It's on. You can go to the website. So again, it's just emi.edu/ and then it's Math Education Resource Center /MERC, and that's technically the Open Math Lab, and it's all online, obviously, but you just find the tutor and set up a Zoom meeting with them, and they can help you. Or talk to each other. I don't know. Find help somewhere along the way. So before we start the new stuff, maybe I'll just see if there's any questions on past homework or homework you've been working on, or questions about life. Returning to VMI in the fall can be an interesting experiment. Any questions on anything? All right, well, interrupt me if there is. I think today is pretty jam-packed as well. I think it's the last day that we double up on a particular section, but yeah. So it's gonna be a full day, but then after that it's just singles from here on out. So this morning it's actually fairly quick, so we also will still have plenty of time for questions or time for you guys to go do homework, which is maybe what you need. So 12.4 is something called differentials. And then 12.5 and 12.6 this afternoon. It's more on derivatives. It's chain rule for multivariate functions and what are called directional derivatives. So like I said the first day of this stuff, you do not have just one derivative anymore. You don't even just have two derivatives anymore. You actually have infinite many. You can go in any direction of the compass that you want, and you'll get a different slope. I think, well, we'll get to it. But really the way to think about it is, suppose that you're out hiking and you're on a mountain. It's going to be pretty rough. You're on a hill and you're standing at the top. Well, if you're standing at the top, no matter which direction you look on your compass, the graph is flat. It looks flat every direction. So in every direction, the slope will be 0. But if you're standing on the side of the mountain and you look down, then you'll have a slope that's down the mountain, and that makes sense. So, if you just turn your compass east, you may be heading down the mountain. If you turn your compass west, it might be the exact opposite. You're going up the mountain. So you have a slope to the east and you have a slope to the west. But if you look north-south, you're actually going to be traversing like around a path around the mountain. So the graph, it looks flat. You're not going up, you're not going down. You might have a slope that's really big up and really down, big negative, or you might actually have slopes here. And then what happens if you look northeast? Well, northeast, you're kind of you're looking that way. So it's not quite as steep because you're not straight up the mountain, but it's also not flat. So any directional point, you're going to have a different slope. So how do you deal with that? That comes up later. In 12.4, we did do this before, so it's always good to look back at what the old approach was. And again, I'll say if you've had class with Colonel Sullivan, who loves this stuff, it's just linearize. It becomes way easier to do these kinds of things. So what that means is if you have a function that's y equals f of x, and x is changing from like one point to another point. Actually, let me not even write h. I'll just use the format that we have. We need delta x there. So delta x is some small change in x. So you might know what's happening at A, but what happens if you tweak it just a little bit? You know what's happening at A plus a little amount. And we're going to do some examples so you can see what's going on. If x changes, what happens to y? So we know that the exact answer is that, well, y is going to be going from f of a to f of a plus this little amount. But the point is that this one right here might be difficult to calculate. So and I know you all have calculators, and that's all well and good, but we're going to try and do some of this stuff by hand so you can sort of see the techniques, the quick and dirty techniques that you might want to use in your engineering classes. So how do you approximate the change from here to here? That'll be how much y changes in delta y. So what we did in the picture is, so you had your graph, y equals f of x, and you are starting at some point where here's x equals a, and you go over, and I'm going to accentuate it because the picture will be too small otherwise. I go over a small amount. We'll call that one delta x. Then the original point, f of a, is here. That's where you're starting, and where you end up is right there. So you go over, and then you go back up to the graph, and you'll have f of a plus that little amount. So this amount right here is how much y changes. So if you change x, you go over, you go back up to the graph, and that's how much y changes. And then you just subtract those 2 points, and you've got your answer. But again, sometimes these calculations can be very difficult. So instead, what we do is we're like, forget the graph. Let's just use a very basic line here, and we're going to actually use the tangent line. So we stick in the tangent line in here, and we notice that this distance is this is going to be the distance that we're interested in here. And that distance right there is called dy. So this is the approximation for how much the graph changes using the tangent line instead of the function itself. And the tangent line is very quick and dirty. It's just a straight line, so y equals mx plus b. It's very easy to calculate with. If delta x is small, we'll notice that delta y and dy are pretty close to each other. So this is, again, this is the exact change, which might be hard to find. Dy is the approximate change. And if delta x is small, then this approximation can be very useful. Of course, I just said on the test, don't round anything. Throw that out for this section. This is all approximation. Okay, it hurts me deep to the core, but I'll survive. And how do you calculate the dy? Is what you do is dy is exactly the derivative at that point, a, and that'll give me the slope, and then I just multiply by the run in order to get the rise. And in that case, the run is delta x. So put a star on that. But that guy right there, dy, is called the differential, not the derivative, but the differential of y. And if you want to approximate these changes, then you can just use a quick and dirty line, and boom, you're done. And I don't know if you remember any of that stuff from Calc 1, yeah, Calc 1, way back in the day, but that's the procedure. Now, how does this extend to 3D? You want to use the slope to calculate approximate changes? Yeah, but you just told me that there's not one slope, there's infinitely many. Well, the cool thing is you can do something that in 3D here, not y, z equals f of xy. You can create something that is called the total differential, or just the differential. That looks very similar. So the total differential of z is dz, just like in the differential for y is called dy. And so before, How did we do this? We took the derivative and we multiplied it by delta x. So now we're going to do exactly the same thing, except there's going to be two parts to it. This will be the z derivative, the partial derivative, times delta x, plus the z derivative, or the y derivative of z times delta y. And that right there is called the total differential. And if the change in x and the change in y are small, then dz will be approximately whatever the change in z is. So we're trying to do exact changes using derivatives to approximate. So how do we do this? Well, let's do some practice here to remember how to even do this partial derivative. So, for example, if you have the function x squared y minus xy squared. And again, I'm going to use this z and f like interchangeably because z and f are exactly the same. If you want to write this as z, that's fine. Just will. So if that is equal to z, we need the partial derivatives, x and y, partial derivatives in order to make this work. So let's see. The partial derivative of z with respect to x. This is where we think of y is not changing. So y is considered to be constant. So we can just pretend that y is a number when we're doing this derivative. So we have a constant multiple of x squared. That just stays as the constant multiple y times 2x. That would be derivative of x squared. For the second part, y squared is the constant and negative 1 as well. And we multiply by the derivative of x, which is just 1. So you get minus y squared. That'll be the partial derivative in the x direction. And then the partial derivative in the y direction will look pretty similar. dz y. We take the derivative with respect to y. The x's are constant, so we just get x squared. Take the derivative of the second one, we get minus 2 xy, or x times 2y. The same thing. So the total differential of z is dz, and it's just the partial derivative with respect to x times delta x, and the partial derivative with respect to y delta y. Now, unfortunately in the book, they'll actually just use dx and delta x and dy and delta y like interchangeably. Because in the last page we saw that delta y and delta x are approximately the same, if they're, and the same thing for the deltas here. So that sort of stinks that we're mixing the notation together. But that's just sort of the way it is. So how do we calculate with this kind of thing? So we need to know some like delta x and delta y, and we need to know what x and y are in order to figure out what this delta dz and delta z are. So in that example, again, z equals x squared y minus xy squared. Or that's equal to f of x. The question is what is something like this? F of 2.04 and 3.06. What is that equal to? So this will be a very basic example because when I first see these two, I'm like, well, just plug in 2.04 and 3.06 and stick it in your calculator. And yeah, that's true. We can do that. But I'm not going to do that for right now. I'm just going to use the fact that, well, if I wanted to figure out what this is, what I can do is I can compute, first of all, an easy one. The function at 2, 3, which looks really close to, 2 looks really close to 2.04 and 3 looks really close to 3.06. And this one's easy to compute because I can just square whole numbers out. And then if I just added on this dz, actually, then this answer right here, this would actually approximate the final answer. So when I say linearize, it really means just find the point that's close and then add on basically how much error you think you have, an approximation for how much change you have. So so first of all, what is the function when you stick in 2 and 3? So if I stick in 2 and 3, I get 2 squared times 3 minus 2 times 3 squared, and that's 12 minus 18. So that is minus 6. And that's what happens if at 2 and 3. Well, what happens if I go just a little bit off from 2 and 3 to 2.04 and 3.06? So that means that I want x to be 2 and I want y to be 3, but I'm going to change x a little bit by 0.04, and I'm going to change y a little bit by 0.06. And so if I use this and I sub it into the dz, that will give me my approximation for how much it changes that I can just add on to my minus 6, and I'll get a good approximation for what the answer is. So rewriting down what dz is. So dz is 2xy minus y squared times delta x plus x squared minus 2xy delta y. And then I just take all this information here and sub it in all of these pieces. Wherever I have x up to 2, y is 3, delta x 0.04, delta y 0.06. And so I will get 2 times 2 times 3 minus 3 squared. And so that's a quick, easy calculation. I just get through. And then delta x is 0.04. Let's plug in. How about if we substitute into this last one here? So we get 4 when we plug in x equals 2 minus 2 times 2 times 3. So 4 minus 12, you get negative 8. And then we multiply that by 0.06. And yeah, there will be some calculation, but this is super easy. There's no squares on this product. Anything in there we're doing with very simple whole number calculations to start. So those calculations are easy. I mean, technically the real answer is not a very difficult one, but don't worry, we'll ramp it up in a second. So that's, when I multiply this out, I get 0.12 and negative 0.48. So that is negative 0.36. And so then the conclusion here is that the function value at 2.04 and 3.06, using my linearization here, my differential is just negative 6, which is the value when I plug in points that are close, and then I just tack on this negative 0.36, and so I get negative 6.36 as my guess. It's my approximation to what the function value is at this new point. Which again, I know looks pretty basic. Plug it in and see if it's even close. And the answer is, it turns out it's within 0.1% of the correct answer. So if you're doing these things quick and dirty and you wanted just a decent approximation, you got it. And in fact, now that I have this answer, now that I have this form, maybe I just rewrite this here on the next page here. So near the 0.23, I know that my function value is going to be 3 times whatever the change in x is, and minus 8 times whatever the change in y is. So that's from the previous slide. I got 3 and negative 8. So kind of like how much it changed in the x direction and how much it changed in the y direction, at least relative to each other. So if I wanted to know what the function is at 2.01 and 3.03 is, then all I do is I just take that -6 where I started and add on this value with the new delta x and the new delta y. So I can do lots of calculations very quickly once I have this set up. This would be just 3 times 0.01 minus 8.8 times 0.03. So I'll get -6 plus 0.03 minus 0.24. So that's -6.21 is the approximation that I'll stick in those values. So you can do some very quick calculations with it. So that's a nice benefit for doing it this way. The other benefit that is nice, so we'll do this one last example and then take a quick break, is what happens if I don't have any numbers at all? And I only have symbols and I want to get a sense of what's actually happening without plugging any numbers in. So here's what I mean. If you look at a volume of a cylinder, you're trying to manufacture some kind of cylinder. The thing is, you need the radius and you need the height. And so the volume of the cylinder, if you don't remember, well, anytime you have a shape like this where it's the same all the way through, you just take the area of the base and multiply by the height. So the area of the base is pi r squared, and then you just multiply by the height. So you get pi r squared h. You don't want to memorize it. That works for any kind of shape. That's called Pappus's rule. Maybe some Egyptian or Greek or something like that to figure that out. So when you're doing this, is this more, suppose you had error in there and you have this like little thing that's manufacturing it, and you have slight deviations in the radius. You don't make the exact same cylinder every single time, which is what's going to happen in the real world. Radius is going to be a little off, the height's going to be a little bit off. You got to figure out what your tolerances are for calculation of this kind of thing. So what kind of, how do you have to worry about this? Is it more sensitive to errors in the radius, or is it more sensitive to errors in the height? If you change the height a little bit, it's going to change the volume. If you change the radius by that same amount, is it going to have the same effect on the volume? And probably you could say, well, look, R is squared, so if I had a little error and I squared it, that would get even worse. And that's true. So you do have more sensitivity in the radius to changes, like little errors in the radius. But how much? Is it like twice as bad, 4 times as bad? Well, this is where you can figure this out. So what you want to know is what the error is in V. So the goal is to figure out what delta V is. But the approximate change in V, by introducing errors in R and H, is going to be is equal to the total differential. dV is anytime you sort of have like a delta, it means exact change. If you have a d, it means approximate change. So the formula for this will be the derivative of v, dr, in the r direction, multiplied by a small change in r. Now here I'm using the fact that I'm going to use dr interchangeably with delta r. I'm going to be using delta h interchangeably with dh. It just makes the equation look a little cleaner. I'm already mixing 2 d's. So that's what we're going to do. This can be interchangeable with calculus. So plus the change in v with respect to h, and then times dh. So that's what the formula says. You take the 2 partial derivatives, multiply them by the small changes in those each pieces, and that's your total differential form. So we can actually do this. What is the derivative of this thing with respect to r? Well, if you take the derivative with respect to r, then h is constant, because this is an r derivative. So I just get 2r. But then I multiply by pi and I multiply by h. So I get 2 pi rh dr. And the other one, if I do an h derivative, then r is constant. So pi r squared in the front is just going to be a constant. I just get pi r squared. Like that. Now, one more step is if I divide by v, then what I'm going to get is, if you take the change in something and divide it by the total amount, then this is the percent change. Maybe not too surprising. You know, if your bank account is $1,000, it goes up by $5. You take 5 divided by 1,000, that will be the percent change. So if I divide everything by v, then that will give me percent changes. So dv over v is the percent change in the volume. Now, what happens if I divide this one by v? Well, I'm actually going to put in what v is. So I'm going to divide by pi r squared h. I'm going to do that on both of them. Because I don't want to mix r and v together on this side. So divide by v, I divide by v, but I divide by what it actually is. What is left when I divide this by pi r squared h? So the pi's will cancel if I divide by that. One of the r's will cancel, and I'll end up getting 2, and I'll have an r in the denominator, but the h's will cancel. So I will get 2, and I'm actually going to write it like this. I'm going to combine these things here, so it'll be 2 dr over r. And we'll talk about that in a second. How about the last one? If I divide this by pi r squared h, then the pi's will cancel, the r squareds will cancel, and I'll be down dh over h. So now we look at this. If dv over v is the change in v, then dh over h is the percent change in h. And dr over r is the percent change in r. So look, no numbers. I haven't put any numbers in for h or r. It's all now into percentages. So the point is if there's a 1% change in the height, that leads to a 1% change in v, assuming r doesn't change. So if there's no percent change in r, then this will be 0. If there's a 1% change in h, this last fraction will be 1, and that'll cause dv over v to be 1. So change h by 1%, the volume changes by 1%. Maybe that's not too surprising, because they're both 1 power, that's a linear term, but that's the deal. How about if you have a 1% change in the radius? So if there's a 1% change in r, assuming that h is not changed, that gets doubled. So the percent change in r is d over r. If I put it into the formula here, I get a 2% change in the volume. So we knew at the beginning that because there's a square, any change in r gets accentuated with the square, but how much? And the answer is it's double. It's double. So squares will cause double change in that. You think about what cubes do and stuff, but that's going to be a little trickier. So no numbers. We use the differential here, the total differential, to figure this stuff out. And we can probably do one more example, but let's take a quick break because we're already pretty far in. And we will do that and come back and chat just a little bit more and then see if you have questions. So say 8:26. We'll see you then.